Each video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises.
In this series of video library modules, we shall discuss the equipment involved in the handling, separation, and treatment of produced well fluids. This first module, PE 121, addresses the components, the design, and the function of wellheads, flow control equipment, flow lines, and surface valves and manifolds. A thorough understanding of the design and operation of this equipment is essential, whether you are concerned with low-pressure marginal wells or prolific, high-pressure multi-zone completions producing under adverse conditions. Bear in mind that improper design or failure of any one of these components could result in loss of life, loss of the well, or severe environmental damage.
In this module, we shall follow the path of the flowing fluid, starting first with the wellhead equipment and moving on to the flow control equipment, the Christmas tree, and downstream flow lines. The wellhead links the downhole equipment to the surface equipment. Wellhead design is predicated on casing design, which in turn is predicated on environmental, regulatory, and production considerations. Standard API wellhead designs are rated for 2, 3, 5, 10, 15, 20, and 30,000 psi working pressures. Factors such as the presence of corrosive fluids and extreme climatic conditions must also be considered. The American Petroleum Institute, the API, sets the standards for the specifications of wellhead equipment. These standards ensure the compatibility of equipment made by different manufacturers. API Specification 6A outlines the basic requirements for materials, pressure and temperature ratings, test procedures, end connections, and dimensions. The major components of a typical wellhead are the casing head, casing spools, and the tubing head. The first casing string run is supported by the casing head, and subsequent casing strings are supported by casing spools. The number of casing spools depends upon the casing requirements of the well. The number of casing strings required for a given well will vary. Typically, they are classified as conductor, surface, intermediate, and production casing. The conductor casing, sometimes referred to as the drive pipe, is used primarily in wet areas or to prevent cave-ins or washouts of unconsolidated very shallow formations. Typically, the setting depth for this pipe does not exceed 400 feet. Often it may only be 40 to 120 feet. The surface casing serves as the foundation for the wellhead. It is generally run to a depth sufficient to protect all freshwater formations, and when set, is cemented to the surface. The intermediate casing string, or strings, may be necessary to prevent whole cave-ins or lost circulation. Under certain conditions, several intermediate strings may be required. The final casing string run from surface to TD is called the production casing. This casing is perforated to permit production or set above the pay section in the case of an open hole completion.
Because the casing head is attached to the surface casing string, it must be capable of withstanding the pressures encountered during drilling until a second casing string is run. The casing head must also support the weight of the subsequent casing strings and wellhead equipment, and it also allows the intermediate string to be centered, supported, and sealed.
Casing heads are available with either threaded or slip-on weld bottom connections. One advantage of the weld bottom is that the topmost casing joint can be cut to the desired height after cementing, ensuring that the wellhead will not be excessively high above ground level. The weld-on casing heads are usually welded at 2 points, one along the bottom of the casing head and the other at the joining of the casing and load shoulder on the casing head. These welds are tested after cooling via a test port. Recently, a process was developed which hydraulically cold forges the casing to a specially machined casing head. For this process, patented by Cameron Iron Works, a combination forging and testing tool is installed. Hydraulic pressure is then applied in the forging tool, which exceeds the yield point of the casing, forcing the casing into grooves machined in the casing head. There are several advantages to this process. Time is reduced, no welding is required, and maximum integrity is maintained. The top connection of the casing head may be a clamp hub, or as seen here, a flanged hub. Flanged connections are generally heavier and stronger. Clamped connections offer faster makeup and lighter weight. The casing head should have two side outlets of the same diameter. Depending on the completion design requirements, these outlets may be threaded, flanged, or have a studded flange or clamp hub. Casing bowls are of two basic designs. One design carries the load of the casing on a load shoulder. The seal area is a vertical metal-to-metal contact area. The other common bowl design offers a tapered seal area, which acts as the seal and carries the load. Metal-to-metal seals are preferred for high-pressure and corrosive environments. Care must be taken to ensure that the seals are protected during drilling and installation in order to prevent damage or possible subsequent failure.
Bowl protectors, sometimes called wear sleeves or wear bushings, are used during drilling and are designed to protect the entire bowl area of the casing head or casing spool from any damage caused during drilling or workover operations. The type of bowl protector required depends on the type of casing hanger and the bowl in use.
The retrievable bowl protector protects the bowl in the casing head housing or spool during drilling. It is installed through the BOP and is landed in the housing or spool and is locked in place by tie-down screws or a locking flange. These screws are located in the flange of the casing spool or housing. The bowl protector is installed and retrieved with a special running and retrieving tool or a combination testing, running, and retrieving tool.
The bit retrievable bowl protector is faster to run and retrieve, but it leaves the bowl exposed to the drill bit when pulling out of the hole. In addition, the driller must always remember to retract the lock screws prior to pulling out of the hole. The casing spool serves a purpose similar to that of the casing head, additionally providing a bottom bowl to seal against the previously set string of casing.
Casing spools are manufactured to meet the same specifications as casing heads. Spools are identified by size, pressure rating, type of bowl design, bottom and top connections, and miscellaneous details such as size and type of outlets and special materials. The casing hanger's primary purpose is to transfer the weight of the casing string to the casing head or spool. There are two generally accepted types of casing hangers: the more common slip-type hangers and the mandrel-type hangers. Slip-type hangers, sometimes referred to as wraparounds, have a tapered back that matches the taper on the inside of the slip bowl. As the casing is lowered, the slips are forced against the casing, increasing the hold or bite on the casing. If extreme loads are to be exerted by the casing string, two sets of slips used in tandem may be necessary. The hanger is hinged, enabling it to be placed around the casing and not over the top. Once placed around the casing suspended in the hole, it is dropped into the bowl in which it will seat. Mandrel-type hangers, sometimes referred to as bowl weevils, are threaded on both the top and bottom to permit placement as the casing string is lowered into the hole. The mandrel-type hanger is a simple design for hanging and sealing off the casing.
The load capacity of hangers must be reviewed before installation to determine an acceptable design. Slip-type hangers can be installed before or after the casing has been cemented, but the casing must be in tension. The installation of hangers is discussed in greater detail in your manual and also in Module P208, Casing Design and Installation.
The installation of the casing head and spools includes the pack-off of each casing outside diameter and the inside diameter of each wellhead component. The term pack-off generally refers to the seal acting in the bottom bowl or the top bowl above the slips, but can apply to all bowls. A typical pack-off would be an O-ring located in grooves in the lower bowl. These seals are effective due to the dimensions of the seal and to extrusion of the sealing element when pressure is applied. Some seals can be activated by injecting plastic into the ports located on the casing spool. A test plug is a wellhead accessory used primarily during drilling. The test plug allows the casing head top connection up through the BOP stack to be tested during the drilling stage. Additional information about test procedures is given in your manual.
Offshore drilling operations utilizing surface-mounted blowout preventers are limited to certain types of bottom-supported platforms. Mobile bottom-supported platforms such as jack-up or submersible rigs can use conventional wellhead equipment and blowout preventers at the surface with the use of a mudline suspension system. The 800 series of the video library will cover offshore and subsea production systems in detail. However, we will discuss the mudline suspension system briefly here.
A typical mudline suspension system for offshore operations consists of a series of concentric casing hangers, each with an internal profile which provides a support or seat for the subsequent hanger assembly. The casing strings extend from the mudline up to the conventional blowout preventers and wellhead equipment used during drilling. After the well has been drilled and tested, a cap will be installed in the mudline system if the well is going to be completed or temporarily abandoned. The blowout preventers, wellhead equipment, and casing from the surface to the mudline system are then removed. When completion work begins, a tree is installed on the ocean floor or on a platform at the surface. A mudline suspension system usually has fluted mandrel or expanding type casing hangers. The fluted mandrel is generally used on larger casing, where casing ID and bit OD clearance is sufficient to allow a support shoulder to be used in the outer hanger. Expanding type hangers are generally used for smaller casing strings where the bit size closely approaches the casing ID. Expanding type hangers utilize spring-loaded steel sections that lock into the mating downhole hanger.
Both types of hangers provide fluid passage for circulating and cementing. Assembly should be furnished with circulating ports which are used during cementing for flushing the landing or the tieback threaded area. Precise landing and tieback procedures vary according to the manufacturer. These details should be discussed and thoroughly understood to ensure proper makeup. If the well operations are to be temporarily suspended, a re-entry plug is placed inside the last casing string run. Following the removal of the casing extensions, a cap is installed, sealing the last string and all subsequent strings. A buoy or other locating device is then placed at the location. Whether onshore or offshore, a tubing head is installed next, after the last casing string has been set and the well has been or will be completed. The tubing head design and function are very similar to that of the casing spool.
The top bowl of the tubing head provides a load shoulder to support the tubing hanger and packoffs. The annulus between the tubing and production casing is accessed through one or both of the outlets on the tubing head. The tubing head and hanger are critical components on high-pressure flowing wells, since this seal is exposed to the subsurface pressure. A mandrel-type tubing hanger is the generally accepted design for supporting the tubing. In high-pressure or H2S environments, an extended neck with a sealing element isolates the tubing head and tubing adapter flange. A hydraulic supply inlet for downhole control lines is generally available as an option in tubing hanger designs. Surface-controlled subsurface safety valves require a hole drilled in the tubing hanger to hold the control assembly with an extended neck to allow a seal in the tubing head adapter. The hydraulic control line extends to the safety valve in the tubing where it connects to a port. A slick joint assembly, sometimes called a hook wall, is often used in lower pressure applications. Here, the tubing hanger acts only as a seal for the tubing casing annulus, and the tubing head adapter supports the weight of the tubing. The design of this hanger allows manipulation of the tubing string to set or release packers and tubing anchors.
At this point, let's briefly discuss multiple completion wellheads. Although as many as 5 intervals may be produced independently, multiple completions are usually limited to 2 zones, occasionally 3.
A dual completion requires a dual tubing hanger of either the split type or the mandrel type. A common split-type hanger incorporates dual-segmented tubing hangers, a tubing head spool, and a dual-bore master valve. The tubing strings and casing annulus are sealed off by energizing the seals by injecting plastic packing into the injection ports in the tubing spool. To provide additional protection against leakage, a seal pad above the tubing hangers can be energized by injecting plastic into the injection ports in the master valve flange. Due to the increased clearance provided in this type of equipment, gas lift mandrels and downhole control lines can be run. The mandrel design includes a parent hanger that suspends two independent tubing hangers and provides the sealing of the ID of the tubing head bowl. The two independent hangers provide the seal between the OD and the parent hanger ID. The mandrel-type dual completion is effective in many applications. However, it does not offer the greater clearance and versatility of the split-type hanger.
Both the mandrel and split hanger types can be machined to accept back pressure valves and to utilize extended neck hangers to seal in the tubing head adapter.
A back pressure valve is used to seal the tubing, while the blowout preventers and Christmas tree equipment are installed or removed. The back pressure valve can also allow fluid to be pumped down the tubing for functions such as displacing drilling fluid before connecting the tree to the tubing head. The valve can be run or retrieved through a lubricator while under pressure. This procedure is typically used whenever work must be done to the components of the Christmas tree.
All of the equipment we have discussed so far in this program is considered part of the wellhead assembly. Let's now look at the components of the Christmas tree, the flow control equipment. As we said earlier, the tubing head marks the transition from the wellhead assembly to the flow control assembly. The flow control equipment must be able to shut the well in, control its flow rate, redirect flow from a vertical to a horizontal path, and allow injection as well as production through the equipment.
The most prominent pieces of equipment in the Christmas tree are gate valves, located directly above the tubing head adapter. These include the master valve, crown valve, and wing valves. Gate valves are full opening valves that are opened or closed depending on the position of the steel gate. This gate has an opening that allows fluid to pass unhindered through the valve body when the openings are aligned. The gate valve is considered the primary flow control at the wellhead and must be operated fully opened or closed. Christmas trees always have one gate valve called the master valve, and commonly two are used. The advantage of a dual master valve assembly is that it allows the top valve to be used for routine operations, while the lower valve is used for isolation, replacement, or maintenance of the upper valve. Each opening and closing of the gate causes some degree of erosion at the interface of the gate and seats. Generally, gate valves are designed so that the seats are separate and replaceable components. Replacement of the seats is not uncommon. Therefore, a gate valve should be chosen with some consideration given to repair or rebuilding procedures. Note that over-torquing a valve in the open or closed position may cause undue stress on the stem and can reduce the useful life of the valve. A safety valve or activated valve is often installed on gate valves to prevent continued flow through the valve when downstream pressure becomes abnormal. The activated valve, termed actuator by the API, is fitted on top of a gate valve and opens or closes the gate valve using either compressed air or pressurized hydraulic fluid. The compressed gas or pneumatic actuator utilizes compressed air or produced gas to operate the valve. This gas pressure is applied to the piston, holding it down into the open position. A spring closes the valve if pressure falls below a predetermined value. Hydraulic valves differ mainly in that hydraulic fluid is used to move the piston. They are more commonly used when the actuator and subsurface safety valve are both controlled by the same system. Above the actuator is the production T, which directs flow from a vertical to a horizontal path. A gate valve is often placed above the production T to facilitate the easy installation or removal of a lubricator. This gate valve is usually called a crown or working valve. On top of this crown valve, or if no crown valve is used on top of the production T, a tree cap is installed. The tree cap provides quick access to the tubing bore for wire line or other operations. A pressure gauge is installed in the tree cap to enable flowing and shut-in wellhead pressures to be recorded. All equipment in the vertical run from the tree cap to the tubing must have an inside diameter equal to or greater than the outside diameter of the tubing.
The next component of the Christmas tree assembly is the production choke. The choke is used to control the production rate. The rate at which a well produces has far-reaching effects, both upstream and downstream of this equipment.
Upstream concerns include possible formation damage caused by factors such as coning or fines migration. Downstream concerns include possible excessive erosion of equipment such as valves, tees, and so on. Correct selection and operation of the choke is very important and allows us to prevent or minimize problems which could occur from poorly controlled production rates. Chokes come in two basic types, adjustable or positive. Adjustable chokes are used primarily during the testing and completion of a well. These chokes can be adjusted continuously during cleanup operations or well testing when frequent changes in choke size are necessary. The positive choke can employ the same choke body as an adjustable choke. The orifice size is controlled by the choke bean installed. A bean can be of any specified size, typically up to a 3/4 inch opening, and is designed to be easily and quickly replaced. Thus far, we have covered the major components of the Christmas tree for flowing wells: gate valves, actuator systems, and chokes. As we said, the design of these components is based on the tubular goods, pressure and temperature ranges, flow rates, and production methods. Let's look at a wellhead for a pumping well. The wellhead design is basically the same regardless of whether the well is flowing or utilizing some type of artificial lift. A pumping wellhead consists of components similar to those of a flowing well. However, due to the presence of sucker rods and relatively low pressures, the tree assembly is different. The basic components of a typical pumping well are blowout preventers, possibly 3, that fit the polished rod, a pumping tee, a stuffing box, and gate or ball valves, followed by check valves. A safety shutdown switch and a pressure gauge are located on the pumping tee assembly. The casing annulus is tied into the flow line so that natural gas can be produced at minimum pressure without interfering with the downhole pump. Other types of artificial lift, for example electrical submersible or hydraulic pumping units, require special design consideration with respect to the wellhead configuration. The design of wellheads and flow control equipment begins with a thorough understanding of the targeted formation and produced fluids. A well data sheet should be completed, specifying general information such as maximum operating pressure, shut-in pressure, temperature ranges, anticipated production rates, and the details of the casing program. In addition, wellhead equipment data sheets for the casing head housing through the Christmas tree should be completed. These wellhead equipment data sheets should specify top and bottom connection size, type, and pressure requirements. The number and size of outlets and the specification of valves, bull plugs, gauges, and so forth should also be included. This data can, and in most cases, should be estimated before drilling operations start. We strongly encourage you to become familiar with API Specification 6A, 15th edition, as a basis for wellhead design. The publication also illustrates the various components, designs, materials, tests, and inspection procedures for wellhead and flow control equipment. Upon completing the data sheets, the engineer can then prepare a design or request a design proposal from a manufacturer using the manufacturer's extensive database of design solutions.
The equipment presented in this unit is the basic equipment utilized on wells. The engineer must be familiar with the equipment and know the limitations of each component under all possible working conditions. In addition, the engineer should be aware that a good design includes installation of equipment that will enable future remedial work to be done with the least difficulty. At this time, please read Section 1 in your manual and complete the appropriate exercises. This unit of the video will address the basic components of flow lines, valves, and manifolds. Flow lines will be discussed in the greatest detail because of the importance of proper flow line design in maximizing well performance. The methods we shall present for flow line design historically have proven suitable under many conditions. However, the viewer should explore and utilize alternative or in-house methods for the primary or comparative analysis.
The flow line is the means of transporting produced fluids from the wellhead to the production facilities. The flow line may be less than 100 feet, or it may be several thousand feet, perhaps miles in length. The design of flow lines is based primarily on working pressures, flow rates, fluid properties, and economics. The maximum working pressure of the flow line must exceed any pressure that may occur at the well or from flow line testing. The pressure drop from the wellhead to the production facilities must be minimized, since production rates are obviously affected by friction losses. The properties of the fluids to be transmitted through the flow line, for example, the viscosity, temperature, and the presence of any corrosive or erosive materials, are extremely important in flow line design planning and must be known in advance. In addition to the fluid composition, the type of flow occurring is very important. Fluid flow through pipe is defined as laminar or turbulent and is based on the shear between fluid layers. In most oil field applications, turbulent flow results in a greater pressure loss than laminar flow. A dimensionless flow parameter, known as the Reynolds number, is used to determine which type of flow exists in a conduit. It has been shown that laminar flow will exist through a conduit that yields a Reynolds number less than 2000. Turbulent flow will exist in a conduit with a Reynolds number greater than 2000. The Reynolds number N sub Re in oil field units is equal to a constant, 928, times the inside diameter of the pipe in inches, times the average flow velocity in feet per second, times the density of the fluid in pounds per gallon, divided by the absolute viscosity of the fluid in centipoise. The method commonly used to calculate friction loss for single-phase liquid flow through pipe, whether that flow is turbulent or laminar, is based on the Darcy-Weisbach equation. In oil field units, the equation is delta P equals a constant 0.0000115 times F, the dimensionless friction factor, times L, the pipe length in feet, times the specific gravity of the fluid, times Q sub L, the liquid flow rate in barrels per day, squared. This quantity is then divided by D, the pipe ID in inches to the fifth power. In the case of laminar flow, the friction factor F is calculated using the Reynolds number, where F equals a constant divided by the Reynolds number. Turbulent flow calculations are based on an empirical pipe roughness factor and the Moody diagram. Techniques explained in your manual.
These equations are valid for single-phase liquid flow, a condition that seldom exists for produced fluids. Nevertheless, these equations may be applicable, and they certainly are useful when applied to such conditions as those present in water injection facilities.
Calculations for determining pressure drop caused by friction in gas lines, where gas flows usually as a single phase, commonly employ the Weymouth equation or the Panhandle equation. The Weymouth equation is generally used when pipe ID is less than 12 inches and pressure is less than 500 psia. The Panhandle equation has proven to be more appropriate in larger pipes and with greater pressures. Let's look more closely at the Weymouth equation, which has greater application in the design of flow lines. The Weymouth equation in oil field units is Q sub G. The gas flow rate in million standard cubic feet per day equals a constant 1.10 times the inside diameter of the pipe in inches to the 2.67 power, times the upstream pressure in psia squared, minus the downstream pressure squared, divided by the flow line length in feet, the specific gravity of the gas relative to air, the average gas compressibility factor, and the average flowing temperature in degrees Rankine, all to the 1/2 power. Equations for multi-phase flow are basically similar to single-phase flow. However, the difficulty in defining the properties of the multi-phase fluid is great. Your manual explains a technique that theoretically calculates pressure drop through a multi-phase flow line. It is a lengthy procedure which, in addition to the theoretical answer, also gives the viewer an appreciation of the many factors that must be considered. Fortunately, there are several additional ways to determine the pressure drop through a multi-phase flow line. These techniques include computer-generated solutions to multi-phase flow equations, actual field data from existing flow lines, and horizontal flow gradient curves. Let's perform an actual calculation using the gradient curves. Horizontal flow gradient curves are used in the same manner as vertical flow gradient curves. The example given in your manual, which will be presented here, involves designing a flow line 10,560 feet in length that will transport 1,000 barrels of oil and 500,000 standard cubic feet of natural gas per day. The flowing wellhead pressure must be 200 psi to obtain the desired production rate. The pressure at the separator, located 2 miles away from the wellhead, must be at least 75 psi. Evaluating a 3-inch ID flow line first, enter the horizontal axis at 75 psi. Proceed downward until the curve for a GLR of 500 SCF per barrel is intersected. At this point, move over horizontally and read a length corresponding to 1,000 feet. We add this 1,000 feet to the flow line length of 10,560 feet to get 11,560 feet. Enter the vertical axis at 11,560 feet and proceed horizontally until the GLR of 500 standard cubic feet per barrel is reached. Read vertically to arrive at a wellhead pressure of approximately 220 psi. This indicates that the pressure drop through a 3-inch ID flow line would be 145 psi. This is unacceptable, since under this scenario, a 200 psi wellhead pressure would be reduced to 55 psi at the separator. Completing the same exercise for a 4-inch ID line indicates that only a 75 psi pressure loss would occur. Therefore, a 200 psi wellhead pressure would result in 125 psi at the separator, 50 psi in excess of the required 75 psi. This flow line design, then, is acceptable, since it ensures an adequate pressure at the inlet of the separator. Flow line design is further complicated by the inconsistent and variable production capacity of a well over its producing life. The rate at which a well is capable of producing is referred to as the inflow performance of a well. The flow control equipment and flow line dictate what the flowing wellhead pressure can be for a given separator or sales line pressure. The wellhead pressure, in turn, dictates what the well is capable of producing. The production rate as it relates to pressure drawdown may be a linear relationship or, more commonly, a nonlinear relationship. Where liquid and gas phases exist within the reservoir, flow rate and drawdown are not linear, primarily because of the relative permeability properties. In addition, the inflow performance relationship of a well will change as reservoir pressure is influenced by depletion or enhanced recovery projects. For further discussion of inflow performance relationships, the viewer is referred to modules PE 102, 103, and 104.
One aspect of flow line design often overlooked is the importance of the selection of the valves, fittings, and pipe ends. These components can cause pressure drops which can substantially affect well production. A variety of fittings and flanges are available to meet the needs of most applications.
A flow line typically consists of several types of valves. These valve types may include a variety of gate valves, plug valves, ball valves, globe valves, check valves, and miscellaneous valves such as butterfly valves. Each type of valve has its appropriate applications and limitations. The gate valves used in flow line design are basically the same as those used in wellheads. The internal components and operation are similar, with the basic difference being in the working temperature and pressure requirements. As in wellhead use, the flow line gate valve should never be used to throttle the flow rate and should be operated either in a fully opened or closed position. Plug and ball valves are basically of similar design. Whether the sealing component is a plug or ball type mechanism, it will operate in an open or closed position with a quarter of a turn. Maintenance and repair are facilitated by the relatively simple assembly. These types of valves are not recommended for throttling because partial opening would expose the ball and seat to high velocity flow. It should be noted that even when fully opened, this type of valve may snap shut under high velocity flow conditions, creating dangerous and undesirable situations. Globe valves offer the primary advantages of being operable in any partially open position and of being available with 90-degree or 45-degree outlets from the valve body. Globe valves must be installed to manufacturer specifications regarding the direction of flow. The direction of flow is indicated by an arrow which is cast into the valve body. Check valves are designed to permit flow in only one direction. The swing-type check valve is the most common and is relatively simple in design and operation. The lift-type check valve is similar to the globe valve. The disc is seated on a horizontal seat where it is guided vertically by integral guides. There are numerous miscellaneous valves that have application in flow lines. The butterfly-type valve is a shutter-like control device that is suited for low-pressure liquid applications. This valve is opened or closed with a quarter turn. The use of a butterfly valve is limited but is excellent for tank inlet and outlet valves. The diaphragm valve is designed so that the flow of fluid is directed over an indented weir that closes the flow when the diaphragm is brought down and compressed against it by the operating mechanism. The diaphragm valve, often termed a motor valve, has found many applications. Because of the various lining materials that can be installed, this valve type has widespread acceptance in the processing industry, wherever corrosion and abrasion may be a problem. This type of valve can either serve as a shutoff valve or as a flow control and throttling valve.
You must become familiar with the design application of these valves, as well as dimensions and strength data, when designing a flowline system. These concerns must be considered to prevent safety hazards and costly mistakes. Your manual presents a detailed description of the types and components of the many kinds of valves employed in flowline design.
A variety of fittings and flanges are available to meet the needs of most applications. Some of the fittings available are elbows, 90 or 45 degrees, return bend, 180 degrees, reducing elbow, 90 or 45 degrees, T's, reducing T's, laterals, reducing laterals, concentric or eccentric reducers, caps, and crosses or reducing crosses. Fittings are manufactured to be threaded, welded, or flanged into place. Threaded fittings are available for most materials and pressure ratings. Welded fittings are common and readily available for the applications just discussed. Since most fittings are installed permanently, welding is often used. The difference in pressure drop through threaded, welded, and flanged connections is not significant.
Despite the intention to serve as a permanent fixture, it is sometimes necessary to open a particular fitting. When an opening is considered necessary, a flange connection is preferred. The subject of flowline and fitting materials and specifications is extremely broad. Conforming to API specifications is of the utmost importance and must be relied upon in evaluating the various flowlines available.
Basically, the method for determining pressure drop through valves and fittings is to convert the effect of the component to the equivalent length of pipe feet or equivalent length in pipe diameters. The Crane Company Industrial Group presented the resistance coefficient K as the number of velocity heads lost for a given valve or fitting. Assuming single-phase flow, the resistance coefficient equals F, the friction factor, times L, the flow line length in feet, divided by D, the pipe diameter in feet. If all the pressure loss values for all valves and fittings are then summed, we can find the total pressure loss occurring through the entire flow line. One technique to correct the single-phase flow calculations for multi-phase flow conditions is to multiply the equivalent length determined for single-phase flow by the factor 5, when the gas-oil ratio is greater than 1,000 standard cubic feet per stock tank barrel, or multiply by 3 when the GOR is less than approximately 500 standard cubic feet per stock tank barrel. The installation of a flow line requires careful supervision to ensure that the line is not damaged during handling, welding, or placement. Onshore flow lines are usually buried below ground level, typically 12 to 36 inches, for safety and logistic reasons. The standards concerning welding methods as well as testing procedures are outlined in API Standard 1104, Standards for Welding Pipeline and Related Facilities. Offshore flow lines are assembled and installed with the use of a special lay barge. These barges are anchored to the seafloor and assemble the line at the surface. The barge can continuously move forward, allowing the line to sink. These barges are equipped with all the necessary stations to store, weld, inspect, and apply corrosion protection to the flow lines.
Once installed, whether on land or offshore, the pipeline must be tested. The testing procedure most often specified is a hydrostatic test. This involves filling the line with water and pressure testing to 100 to 150% of the design working pressure. This pressure test is held for approximately 24 hours. You should familiarize yourself with company policy and conduct all tests as specified.
One commonly recommended practice involves running a scraper or pig, which is slightly smaller than the line ID, ahead of the water. This tests the line for obstructions or other abnormalities that might adversely affect flow line performance. Other methods of flow line inspection are discussed in your manual. Flow line performance can be adversely affected by several things, among them thermal and electrochemical problems. Thermal insulation can be applied to prevent possible heat transfer when transporting hot or cold fluids. The transport of heated fluids may also result in flow line movement due to expansion and contraction of the flow line metals. Thus, expansion joints may be required to prevent costly line damage. Corrosion of a flow line may occur due to factors such as soil composition, bacteria, the materials being transported, even the presence of other lines. Flow line maintenance includes corrosion prevention, both internal and external, prevention of scale and other solid deposits, and periodic tests to ensure flow line integrity. These tests may involve checking for excessive flow line friction, preventive measures such as periodic treatments with inhibitor or scrapers, or the use of devices to detect the external presence of hydrocarbons.
Well, let's begin to summarize. We have introduced the basic components of wellheads, flow control equipment, and flow lines, and discussed the methods of designing and operating them properly. We've provided examples of wellhead design and of flow line design. We should point out again that it is usually wise to work closely with the equipment manufacturers to ensure component compatibility and the safe, cost-effective design of the required equipment. The proper design of this equipment becomes more crucial as production rates increase or as conditions become more adverse. In closing, please read sections 2 and 3 in your manual and work the appropriate exercises. Good luck.